Okay, so here's part two of the intermolecular interactions, and we'll get through it, and it'll be a continuation of what we've been talking about, and also I'll try to apply it a little bit. There's kind of a lot of stuff here, and a lot of it is interesting, and I'm not sure how much I really will want you to know. There will be a multiple choice quiz about this in the next one as well. And we'll see how that goes. And you'll be allowed to use the PowerPoint in your notes for those. Okay, so as well. So we left off the intermolecular forces. You can predict boiling point, melting point, and other things, comparing the strength of the intermolecular attractions. So strongest ones are ion dipoles. Well, actually, if we're so ion dipoles, and like I said, I don't really like to call this a intermolecular because an ion is not technically a molecule. It's an atom, but it could be a molecule, like a polyatomic molecule. And then you have the dipole of a molecule, right? So all of these are all these have in common is these attractions are electrostatic interactions. Okay, so that's what these attractions are. And this is an electrostatic attraction, ionic bond as well. And hydrogen bond is a special kind of dipole. And it actually has, like I said, it has a little bit a combination of like a dipole and covalent character to it. Then dipole is between two polar molecules. Remember, hydrogen bonding is a special kind that goes between a hydrogen that's attached to a highly electronegative atom like oxygen, fluorine, chlorine, and there's a dipole to another highly electronegative atom like fluorine, oxygen, or whatever. Okay, and this is attached to a molecule. So this is a molecule over here, and this is a molecule over here, and the attraction between them is a dipole, but because this is the hydrogen to the fluorine, it's hydrogen bond. Dipole is a dipole, but you can have dipoles that don't have hydrogen bonds in them. And then finally, London dispersion forces, which are temporary dipoles that are formed instantaneous, and they're induced. And the way you can induce them is by increase the number of particles that you have, increase their surface area, and you can increase pressure and increase temperature. Okay, decrease temperature. Those four things will help the induction. The bigger, then, because bigger things are easily polarized. Okay, and so there you go. All right. Physical properties that depend on how tightly molecules packed. Well, compressibility. So compressibility is compacting the particles together. And it's a measure of the ability of substance to be forced into a smaller volume. It's determined primarily by the strength of the intermolecular forces. Gases are highly compressible, and the reason is that is because they can be compressed because they start very far apart, and you can push them together. They have the reason why they're far apart is because, well, for a couple reasons. They're either moving too fast to have interactions, or they just don't have very good interactions. And typically, gases, like at room temperature, are nonpolar molecules that don't have natural attractions to each other. Solids and liquids are almost nearly incompressible, and that's because there's not much volume between the particles anymore. And the reason why they're so close together is because they have strong intermolecular forces. Okay, diffusion. I don't know if we talked about this too much, but diffusion is a random motion of particles and how they diffuse. So it's diffusion basically is a random movement of particles. Gases are diffuse the most. So diffusion's like if you take some food coloring and drop them in water, you'll see that the food color disperse, and this is due to something called entropy, which we're going to be talking about later on in this class. Gases diffuse a lot easier because there's a lot more room for them to diffuse, and liquids and solids there's hardly any room for them to diffuse. So gas particles move a lot more easily than liquids or solids. Okay, diffusion. Molecules travel long distance between collisions because they're very far apart from each other. Diffusion happens rapidly because there's nothing stopping them from diffusing. In liquids, the molecules are closer, there's a lot more collisions, and therefore diffusion is less because they have to traverse between. So, like if this molecule, this particle over here in this gas, there's a lot of space for it to move, and it can move through. This guy over here, it's like going to a really crowded, concert. You want to get to the front stage. Okay, it takes long here. Right here, it's like going to, not so compact, place. Okay, and it's easier to get to A to B. All right. Okay, solids, it's almost hardly any movement at all, but they do move, and we'll talk about that. But you can increase the motion by increasing temperature. So when you increase temperature, you increase the speed of the particles, and they can bounce around more and diffuse more or faster. Intermolecular forces determine strength of many physical properties. Yes, okay. Solids retain both their volume and shape. All right. That means if you have a solid piece of gold, it's not going to change its shape or its volume. And that's because it has strong intermolecular attractions. The molecules are close, and that's because of the attractions. And also, there's that they're allowed to get close because of the shapes and so forth. Liquids will also retain their volume, but they don't have their shape. So if you spill some water, this volume will pretty much stay in the same area, but it won't stay the shape of the bottle. The attractions are still pretty good. Okay, that's why it sticks together. Gases expand to fill their volume. That's because they don't have very good interactions. And also, temperature is a factor, all of these. Again, the molecules are farthest apart in all these different states. Intermolecular forces and temperature decrease with increased temperature. So as you increase the temperature of a substance, you're going to increase the kinetic energy of the particles, so they'll start shaking around. And if they start shaking around enough, they can overcome the attractive forces and break away from the attractions. And if they're allowed to expand, increasing the temperature will increase the distance between the gas particles and decrease the attractive forces. So you will get an increase in volume if you increase the temperature. All right, now we're going to talk about something called surface tension, and everybody's have seen this. It's like if you If you just waxed your car, or if you just take a piece of wax, like a candle, and you put water on it, what it's going to do, it's going to beat it up, okay? And why does it do that? Okay, and the primary reason is that inside the body of the liquid, the intermolecular forces are the same in all directions. So that's like this guy right here. And this guy's connected to this guy, and this guy's connected, and so forth. And so the guys in the middle are all connected really well in all directions. If you notice, this is a round, and it's three-dimensional, so it's a sphere. All right. Okay, now the molecules on the outside, they don't have attractions out here, okay? And so what they try to do is that they connect as close as they can to everything here. And so what that does is all these particles want to get as close to each other as they can. And so what they want to do is they want to increase their interactions. The way to do that is to increase their volume to surface area. So the best shape for any kind of maximum packing of particles is always going to be a sphere, and and that's because a sphere has the best volume to surface area ratio, so you can get the most particles inside a surface area. Well, water has very, very, very tight interactions, and they all like each other. So what they're going to do is try to get close together and create the greatest volume of particles in that surface area. And so if you look at that, that's a sphere, and then that's what this bead is. Okay, so the guys on the outside have higher potential energy because they don't, remember, high potential energy means they're not as stable, okay? And so so by forming this circle here, it creates more interactions inside, and that decreases the potential area energy as much as it can. Okay, it causes the liquid to take the shape of a sphere, and that minimizes surface area to volume. All right, and one reason why it does it on wax is because there's no interaction between. So when you have your wax card, this is the wax right here. Okay, water is nonpolar, so water and wax don't have a natural interactions towards each other, and so the water basically wants to just stay with itself and doesn't want to interact with the wax. Okay, now we tend to call that a hydrophobic type and hydrophilic interactions, which we'll talk about more, I believe, in the next video. Okay, more on surface tension. Liquids containing molecules with strong intermolecular forces have high surface tension. So water has really high, strong intermolecular forces. So an example of that is if you take a column, maybe like a graduated cylinder, and you fill it with water, what's going to happen is that allows us to fill it above the rim. Okay, so now it's different than the meniscus. So one reason, so when you have it's different than this we're saying here. Okay, so what this is saying, if you fill a cup with water, there it does that thing shot again. What it's going to do is you can actually have it, if you fill it all the way to the top, okay, the water all the way to the top, it will actually ball up at the top. And okay, so that's because of surface tension. Now if you have it in terms of like a column, like I was just talking about, the surface tension causes it to form this meniscus. Okay, so and again, surface tension can decrease by temperature, increase because you're breaking apart, you're decreasing the interactions. Okay. Okay, wetting. Ability of a liquid to spread across a surface to form a thin film. So if you take a drop of water and you put it on a piece of glass, what's going to happen to it? And if you take and you put it on maybe like a, not glass, but another substance, maybe this is a piece of plastic glass, what's going to happen? So when you do this, when you put water on a piece of glass, it spreads out. And when you put it on a piece of plastic instead of glass, it beads up. Okay. All right. And the reason why it does that is because the molecules of water can actually form interactions with the sulfur dioxide in the glass, and so forth. So it has some attraction to the glass, so it can spread out. All right. So it doesn't sort of want to. It doesn't feel like it's forced to get away from the glass. Versus this guy here, which is all non-polar. You put it on the water has no natural attractions towards it, so the water just tries to attract itself and forms the bead. Okay, so this is another explaining it. All right, there's things called surfactants, and surfactants can actually cause wetting, do things to spread out better, like water. And those are what we call detergents. And what they do is they lower the surface tension of water. And the way that they do that is by breaking the interactions of the water by interacting with the molecules of the water and breaking the hydrogen bonds. So when it does that, water doesn't. It basically the surfactant, which has a kind of like greasy part to it. Okay, the detergents have a greasy part, and it has a nonpolar and polar part. The nonpolar part will actually be attracted to the greasy glass or the and it'll spread out. Okay, so here's soap. It's just basically a surfactant. And here's just different ones. So they have, this is polar part, and this is the non-polar part. And what happens is that when you put this in the water, this part will stick to the water because it's polar, but this part here will actually stick to the glass. And so, and also it'll break apart the hydrogen bonds in the water. And so the water doesn't really need to be connected to each other as easy as well. Viscosity. Okay, viscosity is resistance to flow. Technically, usually we think of it as like a liquid or fluid. Okay, fluids we usually think as liquids, but turns out there are solids going to have also viscosity, like glass. Glass has a viscosity. The particles in glass, if you could actually watch them, if you could look at the molecules of glass, they actually are constantly always being sinking to being pulled by gravity and sinking. So if you have a piece of glass, okay, the molecules of glass, you can't see them, but are actually moving down the pane of glass. All right, and if you leave it long enough, actually you'll get the glass will have different thicknesses. Okay, so if you get some really, really old glass, it'll be thicker at the bottom than at the top. All right, and that's because the glass particles have moved down. So solids, even though we usually think of fluid as a liquid, it also could be a solid or a gas. And it's related, how the viscosity is related to a couple things. Again, intermolecular forces and temperature. Also called internal friction. Okay, so viscosity is a fluid's natural tendency to not move. All right, so viscosity, or kind of thickness of a fluid, decreases when temperature increases, and that's because the particles start to move around more, and also there's more, gives them more, and it causes more space between the particles. Again, most people associate liquids with viscosity. Like syrup is more viscous than water, but gases can have viscosity. Okay, and then like I said, solids can have viscosity as well. Like if you take, I mean, look at rocks. Rocks will again usually be more dense on the bottom because they effective in because of gravity. Intermolecular forces on viscosity, but it takes them really. So we'll look at two molecules here, acetone. It's just a polar molecule. It has dipole, and London dispersion forces. Okay. All molecules will have London dispersion force between them, but only polar molecules will have dipoles. Ethylene glycol, and we're just telling you this is a polar molecule, but it has hydrogen bonding, dipole, and London dispersion forces. Okay. So which one is more viscous? So which one is going to be able to move? It's not going to be move as well. Well, this guy here, because it has more interactions, and it's thicker because of the interactions. All right, so let's see if we can figure this out. We're given three sets of substances, and we want to know which triplets of these are the most viscous. Okay, so between this guy and this guy, which one is most viscous? Well, I'm going to say this one is the most viscous because it has this here implies that it has a H at the end of a molecule that implies an O attached to it. So this can have a hydrogen bond. So I'm going to say this is the most viscous. These two guys, these two, this is one's going to have more interactions because it's bigger. Both of these are nonpolar molecules. And remember, molecule with more carbons in it is going to be more nonpolar, and the bigger the nonpolar molecules are, the more interactions it will have with each other. And between these two, this guy here is going to have more interactions, again because it looks like it can have a hydrogen bond. This hydrogen will connect to the nitrogen of another molecule, and this one will have both of these are polar molecules. So which one is, so I'm looking which set here, A, B, C, or D. So it's got to be either A or B, and it looks like B. All right. Yay. Okay. So why isn't this look at this has a HO at the end of it? Okay, why wouldn't I think that it could form a hydrogen bond? It can, but the fact that we put the H on the end of it, okay, it tells us that this is the H is hanging off of the O. Here we're not sure where that H is hanging off. Okay, it could be attached to the it's probably attached to the carbon, and maybe not to the oxygen. So it just takes some time to mess around with these. And how do I know this is nonpolar? Because it's all carbons. It has no highly electronegative ion atoms like oxygen, nitrogen, fluorine, chlorine, etc. Okay, and so this one is going to be determined by London dispersion forces. Okay, both of these are polar molecules. How do I know that? Well, I guess you would have to draw the structures to be able to figure that out. Both of these have the same structure. They both have, so these are both trigonopyramidal. Okay. This is ammonia. It has 3 bonds and 1 lone pair. This right here, phosphorus trihydride, it looks the same, but has a P right here. Now, this guy here can form a hydrogen bond with another ammonia. Okay, so what you have here is this. This should be connected to this N here, right? So you have this H is connected to a high electronegative atom, and I said there were 3 that were concerned about nitrogen, oxygen, and fluorine, and it will form dipole to a nitrogen. Okay, this one will form, doesn't do that. It still forms that inner kind of, a P will form with H, but that would just be a dipole. All right. Okay, solubility. Okay, solubility is dissolving substances into a liquid. Okay, for instance, if you take salt and you put it in water and it dissolves. Okay, and so what you do is solubility is a way of making a homogeneous liquid mixture. And why does it occur? I mean, how do we know certain things can dissolve in others? And it could be what we do is we have a liquid in which we're going to be talking about. We did talk about in General Chem 1 when we talked about molarity. With molarity, you'd have your solute, and then you have your solvent. Now, so the solute will dissolve in the solvent, and why is that? Okay, well, one way that we describe that is like dissolves like, and what that means is if you take a polar substance, okay, like glucose. Glucose is polar. How do I know that? Now, in General Chem 1, I told you guys one way to tell if a molecule is polar or not is just look at the chemical formula. Especially if it has a lot of carbons and oxygens. And the ratio of carbons and oxygens is greater than 3 to 1, then it would be nonpolar. It's less than 3 to 1. So if there's 3 carbons to every 1 oxygen, it'd be nonpolar. But you can see here it's 1 to 1, and that way you can kind of tell. It isn't the reason why, but it's a way to identify that the molecule is polar. So glucose is polar. This is its chemical form, right? Okay, so glucose is polar. So when you put it in water, which is also polar, okay, the glucose will dissolve. The reason why it does that is it forms dipole, and hydrogen bonds. Okay, the same thing happens with nonpolar substances. If you take, for instance, if you take oil, like one way that I like to get oil off of things, maybe if I have a oily bike chain or something, and I want to clean it off, what I do is I take gasoline, which is a nonpolar molecule, right? Oil is nonpolar and gas is nonpolar, and so when you put that in, what happens is the oil dissolves into the gas. And it dissolves for a slightly different reason than the polar. In this case, what happens is that the nonpolar, like oil, can fit in between the particles of the gasoline and form London dispersion forces. Okay. So there really isn't a natural attraction, but what happens is that when you, so if you have, so this is, let's say this is your gasoline, and you put oil into it, the oil could fit in between the particles, because you could, and then once it gets in between the particles, it can form London dispersion forces. When you put glucose in the water, it just automatically attracts and gets stuck into the water. But the key thing here is polar dissolves polar, nonpolar dissolves nonpolar. But you can get the other thing, and it's like it does not dissolve. So things that aren't alike won't dissolve, like polar won't dissolve nonpolar. Okay, similar polarity, greater dissolvability. Okay, things with different polarities won't dissolve as well. For instance, oil has a lot lower polarity, it's almost nonpolar, and so it won't dissolve. And surfactants can actually make, like detergents or soap, can actually make these two guys can make nonpolar and polar things interact. Okay, because it's, so if you have a polar molecule here and a nonpolar molecule over here, there's no natural attraction to them. But if you put if you take a detergent that has a polar end on it and a nonpolar end on it, it sort of can bridge the gap between the two and have polar and nonpolar things interact with each other. Okay, which of the following are not expected to be soluble in water? So what we want to look at is polarity. So you have to know polarity. So fluorine is a high. So again, there's different ways you can tell if a molecule is polar or nonpolar. Okay, one way is just, it just takes some chemical intuition and knowing these particles more. But so this is a molecule with just two atoms, and they're two different atoms, and so this is going to be a polar molecule. So this will dissolve in water. Okay, I told you anything that has mostly carbons in it is going to be nonpolar, so this won't dissolve in water. Okay, and this OH at the end tells you that this H here could probably form a hydrogen bond, and therefore it can interact with water. So methane. Okay, what type of intermolecular causes Ki to dissolve in water? All right. So when you put potassium, so the Ki is a potassium iodide. It's an ionic compound, and when you put it in water, what happens is the water breaks apart to two ions. And the reason why it does that is the negative part of water attaches. So negative part of water, which is on the oxygen, is attracted to the potassium, and the positive part of water, the oxygens, are attracted to the iodine. And so what they do is they form ion dipoles. Okay, phase changes. Changes in physical state deals with motion of molecules and attractions. You can change phases by changing temperature. You can have a liquid turn into a gas. And we know what that is, okay? Evaporation or boiling. As heat is added, for instance, if the liquid is water, it forms steam or water vapor. Okay. And we want to look at why that happens. And it requires to change liquid to a gas. It requires energy. So liquid plus heat will give you a gas. Okay, and we'll get into this, but it's in equilibrium, which is a big part of this class. And so this is an endothermic reaction. Okay, if you remember that. All right, so heat is absorbed into the liquid, and you get gas. Solid to gas, sublimation. Okay, and for instance, if you've ever opened a refrigerator and you see looks like vapors coming out of it, and the reason is that some of the liquid has turned into gas. So it skips doesn't turn into a liquid first. It automatically goes right to a gas. That's called sublimation. It's an endothermic reaction. Again, you need to add. So again, add heat. Where was the heat come from? Well, it's just the heat comes from the surroundings. You also may have noticed in dry ice. So if you have a piece of dry ice, the reason why they call it dry ice, it looks like it has smoke coming off of it. Okay, the reason why they call it dry ice is because it doesn't. If you touch it, it doesn't melt. Okay, it may sizzle and give off vapor. All right, so it goes directly from a solid to a gas. Gas to liquid. Okay, you've probably all seen this before. Condensation. You may have in the summertime you go down and your basement, and you'll see that there's water dripping from your pipes, and that's because the warm air and it hits the cold pipes, and it'll cool down the gas to make it a liquid. And so what happens here is that this actually releases heat. Okay. Or another way to think about it is the gas loses heat. Okay, and it turns to a liquid. But it's better to write it like this: gas giving liquid and giving off heat. All right, but one thing you can think about is the gas loses heat, and when it loses heat, the particles can come closer together and form a liquid. Like dew does that. All right, so you notice dew in the morning during the summer, and that's because the warm air will hit the cold ground, and the cold ground will cause it to condense. It's exothermic reaction. And okay. Right, a rate of evaporation. Okay, now let's take a look at this graph here. And this graph here is based on something called Boltzmann Distribution, which we talked about in Chemistry 1. So this curve here is a population of particles at some given temperature. Okay, so and this is a distribution. So this over here is the population of molecules at some energy. So I don't know what temperature this is, but maybe let's say this is a room temperature here. And it says most of the particles, on average, not quite average, but most of the particles will have, this will have the highest fraction of particles will have this amount of kinetic energy. Now so let's say I have a liquid, and the liquid's at room temperature, and here's the population of molecules here. Now there are some molecules that will have this energy and more higher. And it turns out this energy here is the amount of energy that is required to have the particles separate from each other and to be released as a gas. Okay. So this is called, this temperature right here is the minimum kinetic energy. All right. And there's always, so no matter what temperature you have, so at 20 degrees, there's always going to be some gas molecules that, liquid particles that will have the ability to turn into a gas. Okay, so this distribution shape here is dependent on the temperature, and it's called Boltzmann's distribution. Actual Boltzmann Maxwell. Surface area, okay. The more surface area liquid has, more it's going to evaporate. Okay, so, and that should just make sense because there's more of the particles. And the stronger the interactions, so weak interactions will have more evaporation. That's strong. More surface area, more evaporation. So higher temperatures give more evaporation. More surface area gives more evaporation. And weaker interactions will cause more evaporation. But this graph here relates to temperature. Okay, molecules that escape from liquid have a larger than minimum. So, okay, as soon as so there's always molecules. There isn't always just a certain type here. There's some molecules that are gaining energy and some that are losing. So this set of particles isn't always the same, but some are gaining energy and some are losing, but they will always have this distribution. Okay. All right, so when these particles leave, that means is that the temperature actually decreases, all right, because they're taking away, in a sense, they're taking away some of the energy from the temperature, and then the temperature goes down. But what happens is that some guy will come back over here, and the temperature will go up a little again, and then you get this back and forth. Okay, effective temperature on evaporation rate. Okay, so now let's say you change the temperature. If you change the temperature, you'll change the distribution. So this is the new distribution. I've changed, I've heated the increased the temperature. And now you notice is that there's more, the curve is moved further to the right. Therefore, there's more particles that naturally have a higher kinetic energy, because the whole curve shifted to the right, and there's more particles that can escape. Okay, so when you increase the temperature, what you do is you shift the distribution so that there's more particles that have higher kinetic energy, and therefore more have the minimum escape energy. Okay, so let's look at, there's two substances here, A and B, and okay, what we want to do is compare the two. Okay, A has smaller intermolecular forces, and the way I can kind of tell that is because the minimum energy needed is less. Okay. Now these guys have the same curve, but notice they have different minimums. And the reason why they have different minimum is probably because of interactions. Okay. So this guy, both of these have the same temperature, therefore the same distribution, but this guy has a smaller minimum kinetic energy than this one, and the reason why that is because this one it's easier to break apart the intermolecular forces. Okay, and therefore it requires less energy to have escape as liquid, and therefore A evaporates faster than B. Okay, so when you look at these curves, the curves might be the same, but notice is that the minimum is different. And the reason the minimum is different is either maybe because of surface area or because of intermolecular forces. Changes of state involve equilibrium. All right, so equilibrium is something that we're really going to spend a lot of time with in the next several weeks. And so let's talk about it a tiny bit here. And equilibria is that when we look at chemical reactions, we start out that we said the reactions would turn into a product. And we've always made it the reaction as that is a reactant turn into product. And we always thought it's unidirectional. It turns out that actually every single chemical reaction can move back in the opposite direction, okay? Now, now this may but what we mean by equilibrium is that doesn't mean there's going to be the same amount of reactant as product in a chemical reaction. It just means is that we're going to learn more about this. Is that the rate of making P is going to be the rate of making R. So you might have 20 R's over here and then 2 P's over here. But what you're getting is maybe one is turning into a P and P is turning back into an R, and it always has this same ratio. And again, we're going to spend more time talking about what that means. But whenever we look at this change in states, they will always be in this equilibrium where one phase is turning into the other and the other phase is turning back into it. That's if you're at usually this is at a constant temperature. Okay, so there's at the condensed phase, so those is like particles that are all crushed together, and then they come apart like that. Okay, so these guys are constantly falling apart, turning into these, and then if they have intermolecular attractions, these guys will attract each other and turn back into these, and then they'll go back and forth until there's some sort of relationship between the two that will become stable. And like I said, we'll spend a lot more time on that. Okay, so let's say you have a liquid, and what you do is you're going to take the liquid and you're going to pour it into a container. All right, I don't know, maybe let's say you have like some Coca-Cola or something, and you take it and you put it in a container. And what you do is you close it off, right? And so at that point, the liquid is pretty much just a liquid, all right? And what happens is that some of the particles are going to start to escape, okay, because of surface area, intermolecular interactions, and the temperature, okay? All right, and so the liquid is placed in an empty closed container, and it begins to evaporate. Now, those particles are going to be in the gas phase, and the molecules can condense by striking the surface and giving up some of the kinetic energy. So when they hit the wall, what happens is they start to slow down, and then they can condense, okay? Another thing is they actually can come together maybe and form attractions, and they all come back down. All right. Now, a system at equilibrium is when like I said, when the rate of evaporation is equal to the rate of condensation. So that means when the number of particles that are evaporating is equal to the number of particles that are being condensed. Now, doesn't mean they're going to be the same amount of particles. It just means that the change. So there might be like 3 molecules or particles per second that are changing back and forth, but there might be like 50 liquid particles and only 10 gas particles. Okay, but there's 3 that go one way and 3 that go the other way. Always to keep this ratio the same. And one of the key conditions to this is that you have a closed system, right? Okay. Otherwise, the gases would evaporate, and if that's the case, if the gas started to evaporate, there'd be more and more particles escaping. And actually, we're going to learn about this. So what we got here, we got a liquid going to a gas, and a gas going to a liquid, right? Now, if we remove the gas, okay, the liquid's going to... So one of the conditions in equilibrium is try to keep this ratio the same. So if there's, say, like 10 to 2 here, when you have a closed system, okay, and if you open up this system, and let's say you have, let's say there's 400 to 20 here. Okay, so, and that's at equilibrium. And let's say the rate is 2 going back and forth. So if you open it up, what happens is that 2 escape. Now this side will be 18. So this side's going to try to get back to that ratio of 20 to 1. And so there'll be a lot more of these guys going to this side to try to get that ratio. Okay, so the reaction is going to look like it's actually moving to the right instead of going back and forth. Okay. And we're going to relate to that as something called Le Chatelier's principle. Okay, similar equilibrium reached in melting. Okay, same kind of idea happens. Solid begins to change into a liquid as heat is added. So if you take a piece of ice and put it in the water, what happens is the ice starts to melt. Okay, what it does is it'll cool down the liquid, and there will be less. The temperature will cool down, and less of the there will be less energy to let the ice break apart. Then it'll be at some point the temperature will not be able to break apart the ice completely in the water. But what happens is that there will still be and that'll come to a certain temperature, like 32 degrees Fahrenheit. And at that temperature, you get at equilibrium where the liquid turns into a solid. I should say the solid will turn into the liquid. And if you're at constant temperature, if you're at freezing, okay, you'll keep the same amount of liquid. The ratio of the liquid solid will stay the same. Okay. So the key thing is to keep temperature constant. And when it gets temperatures constant, you'll get you'll get a state change, but it'll be the ratios will stay the same. And we'll talk about this more when we get the heating curves. Sublimation, same thing, going to be applied. And then if we look at phase changes, okay, phase changes all in the degree. Okay, from a gas to solid to a gas called sublimation. That requires the most energy, and deposition is the opposite gas going to solid. This requires energy, so this is endothermic, this is exothermic, and sort of these are sort of the ratios. And then the names. Okay, so we got a few more slides to do, so this is going to be just over an hour. And so let's continue. Energy changes accompanied phase changes. All phase changes are possible under the right conditions. Following sequence is endothermic. So solids to liquids require heat. Liquids to gases require heat. So both these are endothermic. Exothermic are the opposite. Gas is condensing. Remove heat. Okay. Liquid to solid, remove heat. Right. What do you have? What we have here is a heating curve, and we're going to say that this is water. And the thing here is that what we're going to do is we're going to add heat and look at what happens to the temperature. So let's say we start here. Okay, maybe let's say this is minus 10 degrees Celsius. All right. Okay. And minus 10 degrees Celsius, water is, and let's say pressure is constant, and say pressure is 1 atmosphere, and it's a solid. Now, as you heat up, so let's say this is ice. As you heat it up, okay, the ice is not going to melt. All right. What it does is you get warm ice. It doesn't melt. But it's still a solid, but what happens? All the particles aren't as close together and as tight, but they're not. They haven't turned into a liquid yet. Just like you're gonna have warm water and cold water, all right? So this kind of thing that kind of messes people up thinks is that if you heat up ice, it melts. Okay, no, it doesn't. Okay, so then when you get to 0 degrees Celsius, the heat that goes into the ice changes state. Okay. All right. It doesn't change the temperature. Now, at that temperature, as long as you're at this temperature, the melting temperature, what's going to happen is this ice is going to turn into a liquid. And it's going to be at equilibrium. So this is the equilibrium. Now, if you keep on increasing the heat, at some point, all the ice is going to melt. And when it melts, now you'll just have one state. So if you have two states, the temperature will stay the same. And that's a pretty cool thing, all right? So if you have ice and liquid together, and as long as there's ice and the water together, the temperature will stay constant. Now, that's if you let it sit and get to its particular temperature. But once all the ice is gone, as you add heat, the temperature is going to start to increase. Now, what you can do is you can heat it up so fast that you can have water that has a temperature that's higher than boiling point. That's called superheating. Won't get into that. But but when you get to in this case 100 degrees Celsius, again, at that point, that has a phase. That's going to be a phase change, and at that phase change, you get the liquid that turns into a gas, and it's going to stay at that temperature as you add heat until all the liquid has turned into gas, and then what you can do is you can heat the gas, and it can get hotter and hotter and hotter. And so you can have hot gas. So I used to think that the hottest you can get water and steam was 212 degrees. But that's only if you have a closed container. So if you have a closed container and you get it to boiling, okay, and you keep the temperature at 200 degrees, so if you say this is water that's boiling, okay, and it's a closed system, and it's at 100 degrees, all right, and it's boiling, all right. So what's going to happen is some of the gas particles are going to boil, evaporate, but some are going to come back in and turn into water. Okay, now if you keep on adding heat, eventually all these gas particles will turn into, all the particles turn into gas. But if you have a closed container and it boils, both the water and the gas will have the same temperature. Cooling curve is kind of the opposite, okay? Same thing applies. You're removing heat. Enthalpy of phase changes, endothermic, you have to add heat. So like when you go from a solid to a liquid, or you melt, you have to add heat. Or delta H is always going to be positive. Okay. All right. This is sublimation, but in this case, it was talked about melting. So to liquid. So if this was a solid to a gas, you have to add heat. Okay. And so the delta H would be positive, and we would call that the enthalpy of sublimation. Okay, if it was if we're going from solid to liquid, we call it the enthalpy of melting or fusion. If you're vaporizing water or evaporating, it's called the enthalpy of vaporization, and so forth. Then you could have exothermic. For instance, so if you go in the opposite directions of deposition, so deposition is going to be going from a gas to a solid. Okay, in this case, it's going to give off heat. All right, we're still going to call it the heat of sublimation, but we're going to give it it'll have the opposite term, negative. Okay. Sometimes it's they call it enthalpy of sublimation or heat of sublimation. Now, General Chem, when we talked about enthalpy, we talked about why that is, and probably talk about it more when we get into thermodynamics. Okay. Right, as T changes, matter undergoes phase changes, and we have some called equilibrium. And there you go, that explains it. You can read it on your own. Okay, liquid vapor equilibrium. Okay, again, if you increase the temperature, you move the curve to the right, you get more particles. They have minimum escape energy. Okay, now this next part's important, especially when we get to the next section. When we talk about applying these principles, we have something called vapor pressure. And what a vapor pressure is that let's say I have a liquid. Let's say you have a container like water. Now at any given temperature, so let's say this is room temperature, some of the water molecules are evaporating. All right. And what they're doing is they're evaporating. The gas is given off. Now, the gas doesn't just go up into space and leave the earth, okay? Unless it's helium, okay? But gravity is going to pull on those gas particles and keep them close to the surface, fairly close to the surface. And then what happens is it says that gas will actually have a pressure excuse my cat there is talking, have a pressure on the liquid. And what that pressure is actually doing, that vapor pressure is pushing down on the top of the liquid, and it's actually helping keeping the water molecules from escaping. Okay, so there's some gas molecules that are escaping, but because of gravity, they're being pulled down, and they're pushing down on the top surface, and so they're having a pressure onto the surface. Okay, and there'll become a point where this exchange becomes the amount of particles that are being released are equal to the particles that are being condensed. That's if you have a constant pressure and temperature. Now, if you increase temperature, what you're going to do is you're going to have more particles escaping, and therefore you will have more vapor pressure. Okay. So what we talk about vapor pressure is usually when it's at equilibrium. All right. So when it's hit, when you stop adding temperature, and etc. So we can measure vapor pressure inside a system, and we use something called a manometer. All right. But okay. So here's different liquids or different vapor pressures. So ether. So let's look at common pressure. Maybe let's look at 760 is normal air barometric pressure. Sorry. Well, let's look at room temperature. Right. Sorry. Room temperature is about 20 degrees C. So let's look at the vapor pressure of all these guys here. So of all these guys here, ether has the highest vapor pressure. That means more of it turns into a gas at room temperature, so there's more gas above the liquid. Water has the second highest vapor pressure, then acetic acid, and then finally propylene glycol. It's a very low vapor pressure. So if you have some propylene glycol, there'll be hardly any gas that's sitting on the top of the liquid. If you have ether, there'll be a high, very much liquid. I mean, a gas just above the surface of the liquid. So ether is very volatile. That means evaporates very easily. So substances that evaporate, things that evaporate will have higher vapor pressures. That's because they form this layer of heavier layer of gas above them. Propylene glycol is non-volatile. Volatile means is that it doesn't change its state. Okay, effect on volume on vapor pressure. All right. So if you have initial volume, there's an initial equilibrium that exists between particles being a liquid and a gas. All right. Now, if you increase the volume, that'll allow more. There's less particles. There's less gas particles that are pushing down on the top of the liquid, and therefore those particles can escape. So the top layer of the liquid is held together by intermolecular forces, okay, and also the temperature, but also by the pressure that's pushing down from the vapor pressure. Now, if you remove that vapor pressure and make it less, Okay, is by increasing the volume is one way to do it. There'll be if you increase the volume, decrease the pressure, kind of like Boyle's law, these particles will be more inclined to evaporate, and therefore you'll get more of the particles evaporating, and therefore you'll have actually eventually a higher vapor pressure inside your system. Okay. Do solids have vapor pressure? Yes. And in given temperatures, some solids, for instance, like dry ice. Okay, that's the easy one. But also solids. Okay, boiling point. Okay, now boiling point's a really important point. It's where the vapor pressure of the liquid is equal to the barometric pressure. And what that means is that when the vapor pressure is equal, so the barometric pressure, that means the pressure of the air that's pushing down on the liquid is kind of keeping those molecules of the liquid in place. That's one of the things that keeps them in place besides the intermolecular forces. Okay, now if this liquid starts to heat up and starts producing its own gas, it's going to counteract and balance out with the barometric pressure. And so the barometric pressure is not going to have any effect on holding these particles together, and then the particles can escape just by breaking apart their interactions, either by heat or mostly by heat. Okay, so once you get to the point where the vapor pressure and the barometric pressure, the vapor pressure cancels out the barometric pressure, and therefore the only thing that you need to do now is break the interactions. Now, typically, if you haven't reached the vapor pressure as less than barometric pressure, the heat has to overcome both the pressure that's pushing down on the particles as well as the interactions. Now, one of the cool thing is that so let's say you take a beaker of water and you put it in a container, and what you do is and it's at normal pressure, maybe like 1 atmosphere. Okay, so here's your water. And okay, and then what you do, let's say we suck out air, and so we decrease the pressure inside the now before we do that, so some of the water is evaporating, okay, but it forms the vapor pressure, but the vapor pressure is much lower, so the vapor pressure at 1 atmosphere is much less than the atmospheric pressure, barometric pressure. Okay, and so what you have to do to have the particles escape is you have to, if you want them, you have to add heat and break to overcome the barometric pressure and the intermolecular forces. But let's say that you start reducing the pressure inside it by a vacuum. So if you reduce that, let's say you bring down the pressure to like 0.1 atmosphere, okay? Right. At that point, the liquid is still giving off the same vapor pressure, okay? But now the barometric pressure is less, okay? In fact, you could be less or even equal. And at that point, you can actually get boiling. And that's at, let's say all of this is at 20 degrees C. So you can boil water at lower temperatures by decreasing its surrounding pressure. Okay, so for instance, if you go up high into the mountains, okay, maybe like at the top of Mount Everest, the pressure up on the mountain is going to be very, very low of the barometric pressure, and therefore it's going to take less heat to create vapor pressure that's equal to the barometric pressure. Okay. Okay. So if you look at periodic table trends, okay, and boiling points, so if you look at water, hydrogen fluoride, and ammonia, and we compare their boiling points, is that water is going to have the highest boiling point, and the main reason why is because of hydrogen bonding. Okay, it has better hydrogen bonding than the other two. Okay, now so that's going across the table. Now if you go down the table, like if you compare H2O with H2S, HSC, and H to these, so if you just look at this column right here and look at boiling point, is that water has the highest boiling point. That's basically because of hydrogen bonding. And then it turns out is that the further you go down, the higher the boiling point. And the reason why that is because of the London dispersion forces. Is that beryllium is a bigger atom. Okay, beryllium is a bigger atom than sulfur. Okay, and it can be polarized easier and can form London dispersion forces. So that's why the curve goes up in this direction. So the bigger the atom, the more likely it is to be polarized and therefore form London dispersion forces. And we'll see that again when we talk about acids and bases, that kind of same relationship. So when you go across, it has to do with hydrogen bonding if all H's are attached. Okay, when you go down or up, it has to do with the size of the atom that's attached to the H. All right, just a couple more and then we'll be done with this. All right, which of the following will affect the boiling point? Right, anything that has to do with increasing, so this has to do with interaction, so this is going to affect boiling. This is going to affect boiling because it has to do interaction. Remember, polarization has to do with London dispersion forces. External pressure on the material, that's like vapor pressure. Okay, that's gonna cause, and so it's all at the top here. Okay, next one, which of the following substances will have the highest boiling point? Okay, this is a solid crystal. This is a gas. Okay, I guess you can have it as a liquid, but it's nonpolar. Okay. Again, one way to tell if it's nonpolar, sorry about the thingy there, is that it's two atoms, the exact two atoms together. So this can be nonpolar. This can be ionic. So this is held together by ionic bonds. These would be held together if they're nonpolar molecules. They're held together by London dispersion forces. This would be a polar molecule. Okay, so this is going to be held together by dipole-dipole. And this is going to be a nonpolar molecule. Again, how can you tell? You have to look at the structure and know more about it. But so if you have a lot of carbon dioxide, they would be held together by London dispersion forces. So which one of these interactions are the strongest? Ionic. So this one is going to have the highest boiling point. This one would be second. And so this one would probably be third, and this one would be probably fourth. How do I know that? This more you know about carbon dioxide. Right, I think that's it. Oh, we got one more, I think. Which of the following substances will have highest boiling point? So which one of these will have the best interactions? Okay, so in this case, you have to look at size of the atom, because so they're all in the 17th column. They're all halogens. Okay, they're all nonpolar. Okay, because they're have the same things attached: fluorine, F2Cl2. Okay, so which one of these is going to have the best London dispersion forces? Well, the biggest ones. So which one of these atoms are the biggest? Well, if you look at the periodic table, you'll see it goes fluorine, chlorine, bromine, and iodine. So iodine is bigger of those four atoms, and therefore this is going to have the highest boiling point. Okay, and that does it. This is kind of a long piece, but again, you can use this to help you on the test that I give. All right, got one more of these, and then that'll finish this material. Then I'll get into that next. Okay, 2 part 3.